Okay, this last problem is particularly interesting. What we have here is a function that has n plus 1 derivatives in an interval containing 2 points a and x, right? And then we introduce this integral, right, that we call Rn of x. This integral is 1 over n factorial. This is just a constant factor. And then we integrate from a to x this term, which contains x, which is a constant to the purpose of the integration, and then t here. So it's x minus t, right? And then the derivative t plus 1. The derivative n plus 1 of f. Okay, so it's a given integral that is defined, well, you define this integral for all integer values of n, including 0. And we assume that this integral exists, right? So that the function that you obtain here is an integrable function. Okay, the first question is we need to calculate a r of 0. Okay, that's the first. That is particularly easy because what we have to do is just evaluate this for n equal to 0. So let's do that. This is 1 over 0 factorial, which is just 1. Then we have the integral from a to x. Then this is 0, so this factor is 1. And then if n is 0, then we have here the first derivative, f prime t dt. And of course, this is a trivial matter. If we are integrating f prime, f is the primitive. So this is just fx minus fa. All right? So the answer is very simple. Now we have to use integration by parts and try to find a recurrence formula for r of n. Okay? Well, applying integration by parts almost suggests itself because you have here n plus 1 derivatives of a function. So this is actually the derivative of the nth derivative of a function. So you already have this as the product of a function times the derivative of another function. So we can, of course, we can apply integration by parts. And if we do that, we get the first term of integration by parts is going to be, this constant is present all the time, right? So it's going to be x minus t to the power n times fn of t, and t goes from a to x minus, okay, then we have 1 over n factorial, of course, because it's present in front of the integral here. Then we have the integral from a to x. Then we have the function fn of t, right? And then we have to multiply by the derivative of this function here, which is n times x minus t n minus 1 times the derivative of this with respect to t, which is minus 1 dt. Okay, let's clear a little bit this mess and see what happens. First, we have this, right? When t is equal to x, this factor here cancels, goes away, right? But of course, if we are looking for a recurrence, n at least has to be 1. So n is larger than or equal to 1. So that means that this is a positive power. So if this is equal to t, if t is equal to x, then it's x minus x 0. 0 to a positive power is 0. So the first term does not contribute. Then we have to subtract the second term, which is when this is evaluated at a, which is fn a over n factorial times x minus a to the n. All right? Now we have this second part. We have a minus here and a minus here, so we have a plus. Then we have an n here and n factorial here, so we have an 1 over n minus 1 factorial. We cancel this common factor n with the n that appears here, right? And finally, what we have is the integral from a to x of x minus t to the power n minus 1 fn of t dt. If you look at this and you compare it with this expression here, you will realize that this is Rn minus 1 of x. So it's this formula substituting n by n minus 1 everywhere. So we found the following recursion. Rn of x, is equal to minus fn a over n factorial x minus a to the n plus Rn minus 1 of x. This is the recurrence and is valid for n larger than or equal to 1. Okay, so the next part, of course, is solve this recurrence. Try to solve this recurrence. So let's see how to solve it. We know the answer of R0, so we know the value of R0. R0 is just f minus fa. So let's try to calculate R1 and see what it is. Okay, R1 is, you take n equal to 1 here, so we have minus the derivative of a, of f, at a. The denominator is 1, of course, and then we have x minus a here. And this one is R0, and R0 is fx minus fa, which I'm going to, fx minus fa. So what is this? Let me write it like this because it's more clear. What we have here is the first order polynomial at a, Taylor polynomial of the function f. So what we have here is the difference between the function and the first order polynomial. And what is that? This is the remainder. Okay, this is the remainder of order 1 of this function. Okay, let's continue, right? We go to R2. What is R2? Well, R2 is equal to minus f second a divided by 2 factorial times x minus a squared. And here we have R1. R1 is equal to this, which is f of x minus the first order polynomial of a. But look at what we have here. We have the first order polynomial plus this extra term, or minus this extra term. That is the second order polynomial. So what we have is f of x minus p2a of x. Again, the remainder of the function minus the Taylor polynomial of order 2. Let's continue. Go to R3. What is R3? Well, it's minus the third derivative of a over 3 factorial x minus a cubed, and then R2. R2 is f minus p2a of x. But look at this, minus the second order Taylor polynomial minus this term is the third order polynomial, Taylor polynomial. So again, this is the remainder of order 3. And we can continue this way, right? And it's clear that what we're going to obtain is that Rn of x is equal to the difference between the function and the nth order Taylor polynomial around the point A. You can check this formula using induction, but it's pretty obvious that this is going to be that way, because every time what we are including here is a new term, which is the next term of the Taylor polynomial, right? So this is trivially 2, right? So this is the interpretation of this. This is the remainder. So what we have here, this formula here, is another formula for the remainder. Remember that we have two previous formulas for the remainder: Lagrange's formula, Cauchy's formula. Now we have this new one, which is an integral formula, right? The interesting part of, or the interesting thing of this formula with respect to the other two, is that the other two depend on an unknown point between a and x, and this one doesn't, right? This one does not depend on any intermediate point, unknown point there, right? But of course, it involves a complicated integral here. Again, this expression, the reason is this expression is useful is because you can derive from this expression sometimes upper bounds, which are easier to derive than using previous formulas like the Lagrange or Cauchy, right? So the usefulness of this formula is the same as that of the other two formulas for the remainder. It's just derive upper bounds for the approximation, the Taylor approximation, right? But this, this is the conclusion. This is another way of expressing the remainders. An important conclusion for this exercise.